Welcome to This Explainer. Today, we're tackling a genuinely fascinating objective, taking abstract theoretical physics and turning it into a physical, indestructible machine. Because, let's face it, when industrial shafts fail, factories literally grind to a halt. So we are going to look closely at the true backbone of power, the advanced design of shafts, keys, and couplings. Here is our agenda for today. 1. The anatomy of power. 2. Metallurgy and industrial standards. 3. Threat analysis and failure prediction. 4. Enforcing strict rigidity boundaries. 5. Keys, couplings, and connections. And finally, 6. The master assembly. All right, let's jump right into Section 1, the anatomy of power, or defining the mechanical battlefield. Before we start calculating invisible forces or stress limits, we have to establish the physical architecture. Our baseline goal rests on a simple governing axiom. Power transfers to transmission, which ultimately creates motion. The entire point here is to safely transmit rotational motion from a theoretical drawing board into the incredibly harsh, demanding reality of industrial applications. And to pull that off, we rely on the stepped shaft. Now, you might be picturing a perfectly uniform, straight metal cylinder, but actually, scratch that. In the real world, a stepped shaft is engineered with its maximum diameter right at the center and its minimum diameter at the ends. This is crucial to properly support transmission elements like gears and pulleys. What's really cool is how these literal steps dictate the entire structural hierarchy of the machine. They provide physical mounting shoulders to accurately locate elements against axial thrust. And you know those rounded internal corners, the stress-relieving fillets? Those are absolutely mandatory. Without them, stress concentrations would quite literally tear the solid metal apart. Moving on to Section 2, Metallurgy and Industrial Standards, forging the optimal shape. Okay, so we've got the optimal shape. Now we need the literal building blocks. Every shaft design starts with material selection, where the carbon content dictates our baseline yield strength and machinability. But we also have to navigate strict ASME codes. Shafts are manufactured from standard diameter steel bars, scaled in standard millimeter increments. This ensures total compatibility and drastically cuts down on machining costs. The real trick, though, is knowing exactly when to upgrade. Ordinary machinery uses your standard medium carbon steels, sure. But for extreme operational loads, we have to deploy high-performance alloy steels laced with chromium, molybdenum, and nickel. When an engineer specifies an exact alloy like that, they aren't just buying fancy metal. They're buying vital insurance against impact fatigue. Let's look at Section 3, Threat Analysis and Failure Prediction, Mapping Invisible Forces. Because honestly, even the absolute strongest, most heavily alloyed metal is going to yield if we don't map the invisible threats attacking it. We have to isolate the power trio, the three primary attack vectors on our shaft. You've got axial load, which are tensile forces pulling the shaft along its centerline, bending moment, the transverse forces causing it to bow, and torsional moment, the pure twisting force. In a running machine, these attacks almost always happen at the exact same time, which means we have to use complex mathematical derivations, like Moore's circle, to combine them into a single stress profile. I really want to highlight this quote from a seasoned professional. Forces are invisible, but their consequences are catastrophic. Our math makes the invisible visible, allowing us to preempt failure before the lathe even turns. That hits the nail on the head, right? It frames our equations not as boring academic exercises, but as literal, physical defense mechanisms. So to predict exactly when a break will happen under these crazy combined loads, we look to failure theories. Because transmission shafts are machined from ductile metals, we rely heavily on Tresca's maximum shear stress theory, rather than Rankin's. Under Tresca's model, failure is governed by shear, and the math here provides a hard, undeniable limit. The permissible shear stress for ductile materials is exactly half of the tensile yield strength. That brings us to Section 4, enforcing strict rigidity boundaries, preventing operational dysfunction. Okay, we've mathematically guaranteed the shaft won't catastrophically snap. Fantastic. But what if it bends? Even just a tiny bit? A shaft that simply bends without breaking is still a completely failed system inside a precision gearbox. The actual deflection has to stay strictly below permissible limits. If a shaft deflects by even a fraction of a millimeter too much, hydrodynamic bearings will literally starve of lubrication, and your wildly expensive gears will just grind themselves to dust. Rigidity is what prevents operational dysfunction.
There are absolute limits to both torsional twist and lateral deflection. Notice how the permissible lateral deflection is strictly bounded relative to the span length between the bearings. The second an engineer gets lazy and stretches that span length just to make assembly easier, lateral deflection multiplies to the third power. No way around it. The golden rule here? Always keep bearings tight and spans short.
Next up is Section 5, keys, couplings, and connections, anchoring the system. Because think about it, our perfectly rigid, incredibly strong shaft is completely useless if it just spins freely inside the gear. We have to physically anchor the system. Enter the unsung hero, the key. A key is a critical element connecting the shaft to gears or pulleys. Its sole purpose is to transmit pure torque and absolutely prevent any relative rotational slip. It's almost always the cheapest part of the whole assembly, but it is the ultimate gatekeeper of the machine's power. And to protect our massive complex assemblies, we use a brilliantly derived industry standard, the 1.57D length rule. By setting the key length to exactly 1.57 times the shaft diameter, we mathematically balance the shear and crushing forces. We are deliberately designing the key as a mechanical fuse. Under a catastrophic torque load, we practically guarantee that the $10 key will fail by shear long before we ever have to extract a fractured, heavy-duty shaft from a seized gearbox. Talk about a lifesaver. Now, what about connecting two entirely separate machine units together permanently, like an electric motor to a hydraulic pump? For that, we use couplings. The harsh reality of engineering is that perfect alignment is a total myth. Thermal expansion and foundation settling guarantee it. Because of that, we utilize bushed pin flexible couplings. That tiny half degree of flexibility they offer is huge. It absorbs shock loads, dampens vibration, and stops high-frequency harmonics from literally shattering the concrete foundation below. Which finally brings us to Section 6, the master assembly, where theory truly becomes reality. Up to this point, we've defined the geometry, selected the metallurgy, mitigated the stress, enforced rigidity, and safely anchored the connections. Let's look at how beautifully this all integrates. An amateur looks at a blueprint and just sees a collection of isolated mathematical formulas. But a master engineer, they see a living, breathing, indestructible system. The stepped geometry actively minimizes stress. Tresca's theory safely dictates the ductile diameter. The strict rigidity limits guarantee gear survival, and that 1.57D key faithfully transfers the power. Every single variable intricately supports the next one. It's like a giant puzzle coming together. So I'll leave you with this final, provocative thought. We know the math is completely sound. On paper, the blueprint is flawless. But can a perfect mathematical blueprint ever truly survive the immense chaos of physical industrial reality without the hard-earned intuition of a master engineer? Something to chew on. Thank you so much for joining me on this explainer, and I will catch you on the next one.